Hello, I'm recording this video for you for section 1, chapter 12, section 1, and the PowerPoint is on Google Classroom. So you can follow along while you're looking at this video on your Chromebooks, or you can pause the video at any time if you need to take a minute and write things down. And I have this little laser here, so hopefully I can point to things. So this chapter is on chemical bonding, and we're going to start to look at how different molecules, what their shape is, and then also how they behave with each other, whether they are soluble with each other or whether they're insoluble. That's kind of our main focus. And so we'll be looking today at ionic and covalent bonds. These are the two main types of bonds. And we will unpeel covalent bonds a little bit more and look at polar covalent bonds and nonpolar covalent bonds. And we've already talked about these in biology and a little bit earlier in the year too. And then we'll be looking at this idea of electronegativity, which we talked about in the last section of the last chapter, some of those trends of electronegativity and how well certain atoms are at receiving electrons, at taking electrons, and how that influences bonding and polarity. So here, this is the definition of a bond, which we already know that it's just the force that's going to hold two atoms together. And it's the interaction of the electrons of one atom and the nucleus, or the protons, the positive part of another atom. And then we have this term bond energy, and that's how much energy it takes to snap the bond. We actually have to put energy in to get that bond to break. And then when bonds form, they release energy. So then we have our two different types of bonds. We have ionic and covalent. We know that ionic bonds are give and take. So one is giving electrons, the other one's taking electrons, and that happens between metals and nonmetals. And we've learned that metals are more likely to give electrons, which is why they're good at conducting electricity. And then nonmetals are good at taking electrons. So that's why they bond together really well. It's kind of a yin and yang. They're oppositely charged, and it's a pretty strong bond. So this would be like the bond in salt, which we've learned about. And then covalent bonds are sharing electrons. And they sometimes share evenly, and sometimes they share unevenly. So if they're sharing unevenly, and if one of them is better at kind of pulling those electrons towards it than the other, that's called a polar covalent bond. And the one that's better at pulling electrons towards it is the one with higher electronegativity. So like we learned last week that fluorine has the highest electronegativity. It's like a 3.96. And so it's going to be able to pull electrons towards it really strongly, even though it's still sharing. It's just sharing unevenly. And then we have nonpolar covalent bonds, and those are the bonds that are equal sharing. One of them isn't better at pulling than another. That means that they have equal electronegativity. So their numbers, their values for electronegativities are the same. And so this is a periodic table with electronegativities on it. So remember, electronegativity is how well an atom can attract an electron to itself. If it has a higher number like fluorine here, 4.0, it's really good at attracting electrons. And that's because fluorine is small, and it has 7 electrons and it wants 8. So it's right next to those noble gases that they're not showing here that have that full shell, and it really wants to have that 8th electron. Plus it's really small. It doesn't have a lot of shielding from the nucleus, and so it's really good at pulling that electron to its nucleus. And then over here, francium at the bottom, or cesium, those have the lowest electronegativities. They're much bigger. They have lots of shells. Cesium here has 1, 2, 3, 4, 5, 6 shells. So it's got a lot of fluff out of the nucleus. And it also does not want to gain any electrons. It doesn't want to attract them. It actually wants to get rid of its electron. So it's not going to be very good at attracting electrons. So if you were to bond, let's say, the cesium's a metal. So one thing that I didn't mention here with covalent bonds is that they're between nonmetals. That's something you'll want to write down also. Ionic bonds are metal and nonmetal. Covalent bonds are just nonmetals. And then you also would have metallic bonds, which are between just metals. So if we were to bond fluorine, which is a nonmetal, with another nonmetal, maybe hydrogen, we would have a difference here. We would have a 2.1 electronegativity and a 4.0. So that would be a difference of 1.8 or 1.9. Okay, 1.9, and that's a really big difference between electronegativities. So that would mean that that would be a polar bond because there's a big difference between their numbers. And that would mean that hydrogen is, or fluorine is pulling really strongly on those electrons. And if you have a small difference, and I'll give you a scale to measure in a second, but if you have a small difference, like maybe you're bonding these two, the difference here, so we have oxygen and fluorine, is only 0.5. So that would not be a polar bond because the difference is so small. So we're looking at those differences between electronegativities, and we're just doing simple math that I can't seem to do today. We're just subtracting. So this polarity is that difference between those numbers, between electronegativities. And this is our scale. And remember, if you need to pause and write things down, go ahead and do that. This is, so different books will have different scales and they'll have different cutoffs. But if we're subtracting those electronegativities, this little symbol here, this is a delta, which means change in or like difference in electronegativity. So if we're doing subtraction here and we find that the difference is between 2.1 and 3.3, that is an ionic bond. If we find that it's between 0.5 and 2.1, that is a polar covalent bond. And if we find that it's between 0 and 0.5, that is a non-polar covalent bond. So that means that they're sharing evenly and there's not a very big difference between their electronegativities. And then this one, they're sharing unevenly, there is a big difference. And then with ionic bonds, there's a huge difference. We're actually bonding metals and nonmetals, and it's not even a covalent bond. It's a give and take. So it's kind of way more extreme. And you can see that shown here. So this is showing like a give and take, and these are separate electron clouds. This one's going to be taking the electrons, making it more negative, and this is giving the electrons, making it more positive. And then this one is more of an uneven sharing, where it's this atom here is pulling the electrons over to it because it has a stronger electronegativity. So we have this some difference somewhere in here. And then with these, the electrons are being evenly shared because there's not a big difference. So if we go back to this table, if we were bonding like a fluorine over here with a lithium, lithium is a metal, fluorine is a non-metal, so that's going to be an ionic bond. And the difference here, 4 minus 1, would be 3. So if we look at our table or our spectrum here, 3 would land right about here. So that's an ionic bond, and that makes sense because it's between a metal and a non-metal. But then if we were bonding, let's say, we can do hydrogen with fluorine again. So hydrogen is a 2.1 and fluorine is a 4, hydrofluoric acid. Our difference there is 1.9, and that puts us right here on this spectrum, which puts us into the polar covalent character area. And then if we were to bond, like I said, these two, oxygen and fluorine, the difference is 0.5, and that puts us right here on this sort of line between nonpolar and polar. So this would be considered a nonpolar bond probably. And some of these books, different books will have cutoffs in different places. I've seen 1.7 as a cutoff. And it's not really black and white. It's on a spectrum. It's kind of gray. So you would maybe say it's more nonpolar or more polar. Sometimes it's not cut and dry and we can't categorize it. But in general, we say ionic is metals and nonmetals. And then these would be between just nonmetals, and they would be less than 2.1 for their difference. And then here's another way to look at it. So this is showing you a polar covalent bond between hydrogen and chlorine. And we use these little symbols here. I don't think I can write, oops. But we use this arrow. This is called a dipole moment. It has an arrow with a plus on the end. So it's pointing to the negative end. So here, chlorine has, it's pulling more of the electrons towards it, and it has a more negative charge. We also use this symbol right here, and this symbol is called a dipole moment. I'm going to see if I can write. I don't see any way to write on this. Oddly, whoops. Oh, I don't know how to get out of here. Okay. I guess I can't write. But you see this little weird symbol that you guys can recreate. You'll have to draw those sometimes. And we're just showing that this side is negative and then this side is positive. And we know that because here's chlorine. I'm back on this previous slide 4. And chlorine has 7 valence electrons. It's going to want to gain that other electron to have 8. So it's like the noble gases that aren't shown here. And it has a high electronegativity. 3 is pretty high. So it's going to pull, when it bonds with hydrogen, it's going to pull that electron over to it. And even though hydrogen, it's still sharing that electron, chlorine is pulling it unevenly. So you have a negative side and a positive side. And it's kind of unequal. But overall, it's neutral. Overall, it's 0. And then here, these are 2 hydrogens bonded. They have equal electronegativities of 2.1. So if you subtract 2.1 from 2.1, that's 0. So that means this is going to be a perfectly non-polar bond, and they're sharing evenly. So we would be way over here on the spectrum, and that would be non-polar. And this is from another textbook just to show you the variation and how they determine the character of the bond. So they cut it off at 1.7, and they're saying it's mostly ionic after 1.7, and then their other cutoff is at 0.4, saying that under 0.4, it's nonpolar. But this book says 2.1 and 0.5. So just kind of some different cutoffs. We will go ahead and use this 0.5, 2.1 rule. But I just wanted you to see that there are different variations of it. And it's not black and white. It's a spectrum. But we'll use 0.5 and 2.1 for our rule. And then here's some other examples. This is another way that we show polar and nonpolar covalent bonds. Remember, these are covalent, so they're all between nonmetals, and they're all sharing electrons. Here we have F2, and it's going to be sharing evenly, so we're sort of showing that sharing of the electrons here, and neither side is pulling either way. And then, and also the electronegativity of fluorine is a 4. So we would say 4 minus 4 is 0. So of course that's going to be nonpolar. And then here we're bonding H and F. H, we saw, had an electronegativity of 2.1, and F had an electronegativity of 4, so that difference is 1.9, and you can see that it's unevenly pulling the electrons over to this kind of hot side. And then lithium and fluorine, we also looked at that example. Lithium had a 1, fluorine had a 4. Remember, lithium is a metal and fluorine is a nonmetal, so that's going to be an ionic bond. We already know that rule. But this is going to be a huge difference in polarity. It's so big that it's actually split right here. It's actually ionic, and it actually looks more like this. These are separate clouds. So that kind of shows you that range, and that it is kind of gray. It's a spectrum, but we can delineate covalent are sharing, and they're between nonmetals, and then ionic is between metals and nonmetals. I think when I first switched to this slide, I said that all of them were sharing, and I wasn't looking at this one. So these 2 are sharing, and then lithium, the ionic one, is give and take. And then here's another way that we can look at it. So remember that when we look at electron clouds, we're not looking at orbits. We're just looking at probabilities of where the electrons might be in space. And we have weird shaped orbitals. So this is another way that we can kind of picture polar bonds, polar covalent bonds. So here we see oxygen and hydrogen, and we see that the electrons are more likely to be over here. There's a higher probability that the electrons are over here and a lower probability that they're over here. And so we call this a dipole moment, and we're indicating it with these little symbols. So these are the dipole moments, and we're showing that it's negative over here and it's positive over here. And we might also show this with that arrow. So we would draw an arrow, and then on this side of the arrow, we would put a little plus sign. So that side is pointing to the negative, and then that side's the plus. And here is a picture of that. So you would put the plus side wherever it's positive, and you would put the minus, or the arrow pointing to the minus side. So here it says dipole moments are when an atom has a negative center, or has a center of negative charge, and which is here, and a center of positive charge, which is here. And we use that arrow to show that. So here's a molecule. This is carbon dioxide. It's a linear molecule, and we'll be able to determine the shapes of these using some of this information. And then we'll also be able to tell if they're polar or non-polar overall, like the whole molecule. Because sometimes, like in this case, we have a negative side here, and we have another negative side here, and the carbon is more positive in the middle. And so overall, this whole molecule is going to be non-polar, but it does have polar parts to it. So you can kind of think of it like a tug of war, and you can think of the arrows sort of pulling toward the negative side. They're not actually pulling, but it's a way to visualize it. But overall, you're going to have like the carbon in the middle is not going to be moving, right? If you have even tug of war people on each side, the carbon in the middle is not moving. And so overall, this molecule is non-polar. And then here's water. So water has more electrons are going to be in that oxygen because it has a high electronegativity. And you're going to see this negative charge up here and a positive charge down here. So it does have polar parts to it, but overall, the whole molecule is also polar because this top side where the oxygen is has more electrons, and the bottom side has more hydrogen ions. So it's a more positive side. And so overall, this molecule is polar. It has a negative side and a positive side, so it's a polar molecule. And this one is non-polar, even though it has polar parts. Okay, so that's all of section 1. I hope that was helpful. If you guys have questions, please send me questions. And we can also, if I'm able to, we can do like a video chat even during class if that helps. All right, I hope to see you all soon.